Remember, you can feel free to send me, those pictures. In fact, yeah, please do send me the pictures, right? So that I am aware what you did on the questions, right? So that we can just check your progress so far. So here's a question here. It's on momentum, right? Before maybe we can take a look at it, right? Let's maybe revisit the concept of momentum and impulse. So real quick, remember that we're saying momentum is the product momentum is the product of an object's mass and velocity, right? So that means momentum is the product of the object's mass and its velocity. So if I know that here's an object, maybe the mass is 2 kg, right, and it's moving to the right at a velocity of maybe 10 meters per second, then definitely I can calculate its momentum to be mass times v, which is 2 multiplied by 10. Then I get my answer as 20 meters per second. No, remember, mass is in kg, so we say kg meters per second. But remember, momentum is a vector. So if I chose to the right as positive, I have to say to the right, okay? So you deal with direction. Good people, momentum is simply the mass of an object times its velocity. So when does momentum change? When does momentum of an object change? Anyone who has an idea to say when will momentum of an object change? Before we talk about the cause of change of momentum, when will the momentum of an object change? So the momentum of an object, right, will change, right? So the momentum will change, right, meaning we are going to have what you call the change in momentum if the velocity changes. Then the momentum of an object is gonna change. It's another thing is that the mass can also change, but it's in rare cases. In most cases that we deal with, it's only this velocity that is going to change. If velocity changes, then your momentum changes. For example, remember our object which we said that it had a velocity of 10 meters per second, right? So imagine the same object, right? It's moving to the right, and then it suddenly maybe hits a wall. Or let's just say it suddenly maybe hits a wall there. So if it hits that wall as it was moving by 10 meters per second, if it hits the wall, it's going to change its speed, and it might happen that it bounces back. So it means if it was here, it was going that side, right? It might happen that now it bounces and is now going to be moving back at a velocity maybe of 2 meters per second to the left. So the fact that there was a bit of change in the speed of the ball, that means the momentum of that ball changed. Okay, so momentum will change if it happens that the speed of the object changes. So if it was moving at 10 meters per second and suddenly decreased the speed, then the momentum has changed. If it was moving at 10 meters per second and suddenly now it moves at 15 meters per second, the momentum has changed. That means you're gonna have what you call the change in momentum. But then, even though we're gonna have the change in momentum, what is also important to understand is what causes the momentum of an object to change. So now we have to talk about what the cause of action. Right? What causes the momentum of an object to change? So causes of change. Number one, maybe the brakes were applied in terms of a car. If you apply the brakes, then the momentum of the object is going to change, because the speed is going to change. It's going to decrease, or maybe it accelerates. If an object accelerates, then the momentum is going to change. And we know, according to Newton's second law, it says that when a net force is applied, the object will accelerate in the direction of the force. That means for us to have acceleration, just like what Miss Simi said, that means a certain net force must have been applied so that the object accelerates. That is the cause for change. Number 3, there are many things. Collisions can also cause an object to change. The momentum of an object to change. So if maybe you had a ball and then it collides with the wall and then it comes back here moving to the opposite direction, that on its own causes change of momentum. So the cause is the collision. Or maybe if it's two cars that were moving towards each other, or maybe another car was at the back, maybe this is a taxi here, and then this taxi, it happens that it's moving that direction, and then what does it do if it happens that it if it happens that it bumps into this car? That means that now, because of that collision, both the speeds of the objects are going to change. Either the speed is going to increase for this car that was bumped into, and then the speed of this one is going to decrease, meaning velocity. So the moment there is an increase or a decrease, a moment there is an increase or a decrease of velocity, then you must know that you are going to have a change in momentum. You're going to have the change in momentum, right? So mathematically, what we are saying is this. Mathematically, oh guys, I don't want to lie, I like this board a lot. It's so smooth. Okay, but then what I mean is that you're gonna have a change in momentum like this. What it means is that we're gonna say, since we're saying a change in velocity causes a change in momentum, that's why we say this is actually like this. Change in momentum is gonna be the final momentum minus the initial momentum. Okay, that is change in momentum. Is the final minus the initial. Initial meaning the momentum that we initially started with. For example, let's just say that this car, as it was moving to that direction, the velocity of that car was around 10 meters. Oh, I know they like 60 kilometers. So let's just say 60 meters per second. After it collides with after it collides with the car, so let me just say here, after it collides with the car, so this is, let's understand that this is before the collision, right? And then here it is after the collision. So after it collides with that car, now the velocity, we're talking about the velocity of this one. Now the velocity of that guy, it happens that now it is 35 meters per second, still forward. The fact is that the speed has changed, so we will call this one the initial speed, and then we'll call this one the final speed. Final velocity, initial velocity. So that is why when you calculate the final momentum there, we say mass times this final speed or velocity, and then the initial one is going to be what? Mass times the initial velocity. Do you realize that the mass has not changed because the car has not changed? If the car was 600 kg, it will still be what? 600 kg there. The mass does not change. What changes is the velocity. So because the velocity changed from here to there, then we say there was a change in momentum. And to calculate a change in momentum, what do you say? You say final momentum minus initial momentum. Then you say the mass times final velocity, and then minus the mass times initial velocity. But make sure that you choose direction. So I'm gonna say going forward or to the right is positive. Make sure you always choose direction. If we don't see direction there, you will be in big trouble. Okay, so if forward is positive, if I were to calculate then the change in momentum here, I would then say the mass is 600, and then times the final velocity, which is 35, and then I say minus the mass, which is 600, times the final velocity, which is the initial, which is 60. Then from there you would get your answer. Please do punch that in a calculator and please tell me the answer that you get. Then that would give you your change in momentum. That means the momentum has changed. The answer here is gonna tell us the momentum changed by how much. Okay, that's what the answer is going to tell us. Yeah, please do punch it in, guys. Now that we know that there is a change in momentum, and we know the causes for the change of momentum, right? That it could be like, it doesn't mean that it's only these causes. There are so many other causes out there, guys. So we are just naming these ones as a few from many. Okay, thank you for that answer. So you're saying it's negative 15,000. Negative 15,000, if I saw correctly. So that tells you that the change in momentum is what? Is 15,000 kg meters per second, where in the opposite direction. In the opposite direction. Okay, so that's what we mean there. Okay, and then from there, that because the momentum is negative, like the change in momentum is negative, if the answer that you get there, if the answer that you get is I don't want to say if it's negative it means that, if it's positive it means that, but I just need you to understand this analogy or the following. Since it's negative, it's negative what? Negative 5,000. What is this one doing? Yeah, negative what? Negative 15,000. We said forward was positive, so because here we are saying negative, that means the speed decreased. That negative there, the one that you see there, it tells you that the speed decreased. Okay, means the speed decreased. The speed decreased, right? That's why you're getting it as a negative if you chose forward to be positive. But remember, I can choose forward to be negative, right? And then if I chose forward to be negative and then I get my answer as positive, it will still mean that the speed decreased. But I guess from the velocities themselves, you can tell that the speed decreased. Okay, so that is what we have. And remember, I said there are many other causes for change in momentum, for momentum of an object to change. Right. And momentum, change in momentum, by the way, aligns very well with Newton's first law and Newton's second law. Because remember, in Newton's first law, it says the object will remain in a state of rest, or it will continue moving at constant velocity unless a net force acts on it. So that means that if an object was moving, that object is going to have momentum. And if it was moving at constant velocity, that means technically it's gonna have momentum since it's a certain velocity. Then when a net force is applied to the object, the velocity changes and then the momentum will also change. Now, in terms of collisions, now if you have an object A and then object B, what happens? Because we said collisions are also causes of change in momentum. Why are we saying they are causes of change of momentum? Because if this object is moving in that direction and this one is moving in that direction, what will happen is that when they collide, the momentum of A is going to change and the momentum of B is going to change because the speeds are going to change. Now we have what you call the, let me write it here, the is it the law or is it the principle of conservation of momentum? But it's linear, né? So we're dealing with linear momentum, by the way, so we must write that is the linear. So what does the principle of conservation of linear momentum state? Remember, it states that in an isolated system, the total linear momentum is conserved. Okay, the total linear momentum is conserved. That's what the principle states. It states that in an isolated system, the total linear momentum is conserved. What does that actually mean? To say in an isolated system, the total linear momentum is conserved. Well, what it means is that essentially momentum is really not just destroyed or lost, okay, in an isolated system. A good example is if you are on a pool table. If you've played pool before, it looks like this, isn't it? That pool table is gonna have some stuff here, then some holes there, like this, like this. So this will be like a pool table. On a pool table, remember that this background is green, right? It's like a like that surface there, that will be green. So because it's very smooth, it almost represents an isolated system, because remember, this thing happens in an isolated system. So an isolated system means there are no external forces such as, so there is no frictional force, there is no frictional force, there is no applied force, there is no applied force, and then there is no tension. Okay, and for you to remember that, we always say that an isolated system is a system that is fat free. The system that is what? Fat free. When we say fat free, what do we mean? We mean that there is no frictional force, there is no applied force, and then there is no what? There is no tension. I had listed them here. Okay, so if a system is fat free, meaning there is no frictional force, applied force, and tension, that means that the system is an isolated system. And in that type of system, the total linear momentum is always conserved. That means that what this means, this statement, it says that the total linear momentum is conserved. What that means is that the momentum, the sum of momentum before the collision is going to be equal to the sum of momentum after the collision. That means momentum is not like lost, and goes out of the system or something. Sum of momentum before is equal to the sum of momentum after, which simply means that the momentum of A before and after, or the momentum of A plus the momentum of B before the collision, is going to be equal to the momentum of A plus that of B after the collision. What I'm saying is this: the momentum of A, if you calculate the momentum of A here using the initial velocity, which means before the collision, then you add to the momentum of B before the collision again, the answer is going to be equal to So remember, all of this is happening before. The answer is going to be equal to the momentum of A plus the momentum of B. When? After the collision. That is what the principle is saying. So the sum of momentum before the collision for both the objects is going to be equal to the sum of momentum after collision. And good people, please know that this principle applies on two objects which are colliding. It doesn't apply on one object, it applies on two objects. Momentum is conserved for two objects, not for one object, not for three objects. For how many? For two. But three is not, we don't really deal with three objects in grade 12. So hence I'm emphasizing that it's for two objects. The total linear momentum is what? Is conserved if the system is what? Is fat free. Which means the sum of momentum before the collision plus the sum of momentum after the collision of your two objects is going to be equal if the system is fat free. There is no friction, applied force or tension. Alright, I hope that was clear. So how do we apply what we just learned in a question? That brings us to the question that we gave you here. So we are told that we have Pacey there. This one, how do I remove this? Oh, let me just put it here. I'm gonna need it. Right, Pacey, who has a mass of 75 kg, rides at 20 meters per second on a quad bike, which is a motorcycle with 4 wheels. I hope you know a quad bike. Now, on a quad bike with a mass of 100 kg, let's understand that we are given the mass for Pacey and then we are also given the mass for the quad bike. Then what happens? He suddenly applies the brakes when he approaches a what? A red traffic light on a what? On a wet and slippery road. This is an indication that we are dealing with a fat-free system. Why? Because if the road is slippery, that tells you that there is zero friction or minimal friction. You see? So we're dealing with a fat-free. Because remember, our principle only applies on an isolated system. Now we are then told that the wheels, right? The wheels of the quad bike lock and the quad bike slides forward in a straight line. The force of friction causes the bike to stop. The force of friction, right, causes the bike to stop. In what? In 8 seconds. Causes the bike to stop in 8 seconds. So what type of situation is that? Here's the road here, and then I'm quickly gonna draw a bit of nice traffic lights here. I told you guys I like this board because I'm able to draw nicely. So here is our traffic light there, and then that traffic light is gonna have a red, red, yellow, and then we're gonna have green. Nice traffic lights there. Let's assume that there is no load shedding. So we have red, yellow, green on our traffic lights. Now, here is Pacey, right? So let's actually draw the quad bike first. So the quad bike has 4 wheels. Yeah, that's gonna be something else. The quad bike has 4 wheels. 4 wheels. Guys, you can't do me nothing with drawing. Nah, shame, you can't do me nothing with drawing. Check. Yeah. So let's have Pacey there. Probably is gonna be sitting Pacey, isn't it? So let's draw him sitting there with his legs inside, and then he's holding onto the bike. Buffet. Nice, just that I didn't pass drawing nicely, but it's because they were a bit jealous of my drawings. So look at this, right? This is Pacey there. Let's say the mass of Pacey. Remember, let's just call it M of P, P for Pacey. The mass is 75 kg. And then the mass for the bike itself, right? So the mass of the quad bike, so let's write it as mass of B. The mass of B is how much? Is 100 kg. Okay, it's 100 kg. Let's take our traffic lights a bit back, right? Hoping I'll be able to move it. Let's take it a bit back, maybe this side. Right. So here's Percy, and then he's on his quad bike. He's approaching the traffic lights. Then when he realized that no, the traffic light is saying red, 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 man, red, what does he do? He applies the brakes. He applies the brakes. He applies the brakes. And when he applies those brakes, let's just show them nicely here like this, to show that there is now a bit of friction there. So when he applies those brakes, here is gonna be his motion, isn't it? You know, so we can apply them here. He was going well, and then he was going fast, and then he applies the brakes, you know, to try and avoid him hitting there. Okay. So for around 10 seconds, he stops in what? In 10 seconds. The force of friction causes the bike to stop. Oh, so that means here there is actually what? Friction there. There is friction. So that force of friction causes the bike to stop in 8 seconds. So that is happening in what? The time there for the bike to stop is around 8 seconds. So this is when he's applying the brakes there. Right. I hope that the scenario is clear, because you must always have a good picture of the scenario. So let's talk about the velocity. The velocity for Percy, the initial velocity for Percy is how much? Is 20 meters per second. But can anyone tell me, because we are not given the velocity of the quad bike, what is the velocity of the quad bike? The initial velocity. Okay, so you're saying 20? Okay. That is true. It is 20. So this one is the initial velocity, but for Percy. So usually how you write it, So you can write it like this. Just fix it. It is the initial velocity, but for Percy, right? So I'll write P there. And then the initial velocity for the quad bike. So I write initial, and then, actually it's velocity for B, and then you write initial. What am I writing? Velocity for the bike, but the initial one. Here we should also fix it. It's velocity of Percy. But the initial one. Yeah, now it makes much more sense. So that velocity for the quad bike is also 20 meters per second. Because of what? Like I said, Newton's first law. Newton's first law says that a body will remain in its state of motion at constant velocity unless a net force acts on it. So here we are literally talking about a constant motion, because the velocity was 20 meters all along. It was not changing. So the velocity of the car will be the same as the velocity of the person in the car. Same way here, the velocity of the quad bike will be the same as the velocity of the person on the quad bike. Alright. Then now they say define the concept momentum. I think this one we then said it, right? We did say that momentum is the product of the mass and velocity of an object. The mass and velocity of an object. Okay, perfect. Then they say calculate the change in momentum of Percy and the bike from the moment the brakes lock until the bike come to a stop. Yeah, change in momentum of Percy and the bike. So we are treating them as a system there, to say what is going to be the change in momentum. So that change in momentum, right? How do we calculate it? Remember, change in momentum is equal to the final momentum minus the what? The initial momentum. Remember, applying brakes causes a change in momentum, like we said before. So there's definitely a change in momentum. So we have to calculate it. But for us to then say final momentum minus initial, we just take forward as positive, okay? So we're going to take forward as positive. Then you say mass times VF minus mass times VI. That's going to give us the change in momentum. Now remember, Pacey and the quad bike, right? We are treating them as a system, right? As one system. So what we would say is that therefore, the change in momentum, can I please finish it off here? The change in momentum is going to be the mass. What will be the mass now? Okay, let me just write it here. I feel like the space is gonna be a bit small. So the mass now is going to be 100 plus 75. You're not gonna write 100 only there. If you write 100 here, you're calculating the change in momentum of the quad bike. But if you write 75 here, you're calculating the change in momentum for Pacey. They said calculate the change in momentum of Pacey and the bike. So both of them. So it's going to be how much? It's going to be 175 kg. And then the final velocity is going to be what? Obviously, remember the bike is going to stop. So you're going to put it as 0. Then you say minus. The initial one, you say 175. And then the velocity should be how much? Should be 20. So now, what do we get as the answer? 175 times the 20, you get your answer as 3,500. Yeah, so you get it as 3,000, but it's going to be negative 3,500. Remember the units is kg meters per second. So that is how you calculate that. So remember, you finish off by saying 3,500 kg meters per second in the opposite direction. Then that would be your momentum then, the change in momentum. So guys, I hope you now understand what is change in momentum. It is simply looking at how the velocity changed, because the mass will not change. Pacey and Pacey and the quad bike is going to be they're going to have the same mass, and that mass is not going to change, but what is going to change is the velocity. That is why it's crucial to understand that momentum changes when velocity changes. Okay, so that is why we use the initial velocity and the final velocity. What tells us that the final velocity is 0 is the fact that we were told that the force of friction causes the bike to stop in 8 seconds. So stopping tells you that you're gonna have your final velocity as what? As 0 meters per second. So that's why we put it there, and then now that's why we get our answer. Okay, so I hope that was clear. A very, very nice question there. I hope that you got it correct. I would really love to see your answers. Remember, please do send them to me. The ones you wrote before, by the way. Please, I'm begging you. All right, so that is how we deal with the change in momentum. So sometimes, let's go back here. We did say that we can have two objects and then they are colliding. That one there was not really about objects colliding. The one whereby we have objects that are colliding, we can have it from this. So let's just say you did have two objects, and then the other one, let's just call it A. It's going that side at a velocity of 6 meters per second, right? And then we have a B, which is moving this side at a velocity of let's just say 8 meters per second. right? So then the mass of A, you are given that the mass of A, let's just say it is 2 kg, and then you are given that the mass of B is around 8 kg. So we want to know if these things, they collide, isn't it? They collide like this. We want to know whether we're gonna have any of these cases. Are we going to have that they will be stuck together and then they move as a unit to that side, or they get stuck together and then they move as a unit to that side? Or are they going to separate? The other one is gonna go there and then the other one is gonna go there, or they are going to stop? Which case is it going to be? For you to know which case it's going to be, you need to use the principle of conservation of momentum. Here I want you to assume that the system is fat free, meaning there's no friction applied force and tension. And I need you to also realize that, remember that last question we did have friction, right? That is why there we didn't need to use the principle, but it is also because the two objects that are colliding are not there. You understand me? It's just Percy and his quad bike. We take that as one thing, right? If maybe Percy had stood up and then he jumped from the quad bike, the bike goes that side and then he goes on the other side, or as long as he was to separate from the bike, then we would treat them as two objects. But because he's all the way sitting on his quad bike and moving with it, we just treat this problem as having what? One object only. So you only have one object there. We don't have two objects. We can only have two objects if Percy maybe stood up from the bike and then he left it. Okay, so that is why here we're not talking about the principle of conservation, but merely we're just discussing the change in velocity, which is the change in momentum. This time now on this problem, what do we have? We have two objects, and then now since there are two objects, we can talk about the principle of conservation of momentum. So these two objects, they're going to collide. So we need to know which case are we going to have. For you to find out, isn't it interesting that you get to get information and then you can actually determine whether you have this case, that case of that or that. It's actually a nice thing, guys. I mean, I would enjoy doing that. So let's find out, shall we? So for us to find out, it's very quite simple. The first thing we'll need to do is to choose direction. We already know that here it's either left or right. So I'm gonna choose to the right as positive. I'm gonna choose to the right. Anything going to the right will be positive, meaning anything going to the left will be negative. So what do we do? Remember, the principle says the momentum of A plus the momentum of B before the collision will be equal to the momentum of A plus the momentum of B when? After the collision, if it's an isolated system. I did say that we treat it as an isolated system here, according to the question that I'm saying we assume it is an isolated. How do we calculate momentum of A, guys? Momentum of A, remember, momentum is mass times what? Times V. But those things, you need to assign them letters to show that this is the mass of A or mass of B. So I'm gonna write mass of A, velocity of A. So I'm talking about this. And then because of this I, it's like I'm multiplying it inside. So here I then write what? I then write I. That's why I like to write it like this. It will remind me that this I must put it inside so that I have initial. Same thing here. Momentum of B is the mass of B times the velocity of B. Then when I put this I there, I'm gonna have what? Initial there. Good. What is momentum of A? It's the mass of A times the velocity of A. But this F outside reminds me that it's final. While here, the mass of B times velocity of B, but then the final velocity there. You see? That's why I like it in this form. Then now I can simply substitute. What is the mass for A? The mass for A is 2 kg. Remember? It's 2 kg. So I write 2. What is the initial velocity for A? it's going that side initially. Oh, what we are told, by the way, is that after collision, because this is all sorry, see, all of this is before, is before. So what we are told is that after collision, B is going to that side at a velocity of sorry, we're told that B is going this side actually at a velocity of 1 meters per second. That's what we are told. So initially the velocity of A is what? Is 6, but it's going to the right, which means it's positive. And then I say plus. The mass of B is 8. The initial velocity for B is 8, but it's going to the left, so I write negative 8. And then mass of A is what? Is 2. Remember, the mass does not change. But now the velocity of A, I don't know where it is going, so I'm just gonna write this. And then the mass of B is 8. The velocity of B is what? Is negative 1, because now we're told that B is going to the left at 1 meters per second. Then I can solve for that. Could people put that in your calculator? So I believe you're gonna have like 12 minus 64. Yeah, so it's gonna be like negative 52, and then this side you're gonna have 2 VAF, and then you're gonna have minus 8, and then when you take the 8 to the other side, you're gonna have yourself negative 52 plus 8 being equal to 2 VAF, which means that you're gonna have negative 46 equals to 2 VAF. You divide by 2, you divide by 2. Did I make a mistake here, guys? Therefore VAF will be 23, negative 23 meters per second. Does it look correct, guys? So what does this negative 23 mean? It means that the velocity of A final will be 23 meters per second to the 23 here to the left. Right, that's what it means there. And it does make sense because the mass of B is very large. So probably when it hits A goes backwards that side at a very large speed of what? Of 23 meters per second. So that's how you calculate the change in momentum. Good people, if you have this, if you know this, there's no question that should give you problem. Whether it's problems that are separated or comes as a unit first or what, when I just focus on what is the mass of A, what is the mass of B, what is the initial velocity of A, what is the initial velocity of B, and then what is the final velocity for A, or what is the final velocity of B. You should have at least one of those, and then you'll be able to solve your problem. So any questions from there, guys? Right, I really hope that it is clear. So yes, talk to me.
Isn't V final going to the left?
Yeah, it's
The
going to the
opposite.
left.
So is it not minus A?
Here, remember here I wrote it as minus, ne? Then down here, instead of writing minus, I wrote left, because the minus only indicates the direction. Do not write negative 23 meters per second left. If you write minus, you don't write the direction. If you write the direction, don't write the minus. Yeah, what? Because the minus is saying left. Do you understand me? Great.